Hi, this video lesson today is designed to look at some of the conceptual pieces of free fall motion as well as how we spin the mathematics from horizontal, one-dimensional kinematic motion into vertical, one-dimensional kinematic motion. Now, what we see here, right, when an object falls, right, the idea of it falling means that it's going to be moving vertically, and we define free fall motion as an object that is falling and is solely under the influence of the force of gravity, right? We do not consider any other forces when we're looking at free fall motion. It is strictly the force due to gravity that is pulling down on it. We ignore air resistance, we ignore wind, we ignore all of that stuff. Now, being in free fall, right, tells us that every single object will accelerate at the same rate. And that acceleration is the acceleration due to gravity, which in shorthand we write as a lowercase g. And we consider that acceleration to be constant on the surface of the planet. If we get further and further and further away from the planet's surface, we see that acceleration start to shrink a little bit. It doesn't shrink much, right? But it does get smaller the higher your elevations are. And it gets higher as your elevations come down. So in free fall, rather than looking at A as our acceleration from horizontal motion, now we can consider it to be G, which is really nice because we're going to know what G is at all times. In horizontal motion, you didn't always know what that acceleration rate was. When we're talking vertical free fall motion, again, specifically free fall when it's solely under the influence of the force due to gravity, right, of the force of gravity, we are always going to know G. Near the surface of Earth, G, the acceleration due to gravity, is negative 9.81 meters per second squared, which tells us that every single second that passes, that is how the velocity will change. So if you throw something up is going to be defined as the positive direction. Its velocity will slow down at a rate of 9.81 meters per second squared until it reaches its maximum height, with which that velocity will go to zero. Then, as it starts to come back down to the surface, its velocity will then increase by 9.81 meters per second squared. And it comes down to this plus and minus at the bottom here. Anytime we have movement up from some arbitrary point zero, we're going to consider that the positive direction. Movement down, we're going to consider negative. All right, so typically, if you have a ball and it's in your hand and you throw it vertically, right, straight up in the air, its height is going to be considered positive, its velocity will be considered positive, but the acceleration will be negative, which is going to slow that ball down on its way up to its maximum height. Then, once it reaches maximum height, we are going to be at a velocity of zero. There's a moment in time where that object, whatever it may be at maximum height, is going to be at rest vertically. It stops moving up, and it's not quite moving down yet, right? It's going to hit some vertical velocity of zero. Then, as it begins to fall downward, this object will be moving downward. Its acceleration will be negative. Its velocity will be negative because of that direction. So we're going to see that object, whatever it is, in this case I gave a ball, it is going to speed up on the way back down. So by technicality, this free fall motion begins the second the ball leaves your hand, right? Anytime an object is thrown into the air, it is in free fall as long as nothing is in contact with it and we don't consider other forces outside of the force of gravity. So again, you throw something up in the air, it leaves your hand, it is now in free fall motion. Even though it is moving upward, it is considered to be in free fall. Slows down on the way up, reaches the max height, gets to zero for its velocity, then it speeds up on the way back down. So our free fall equations don't look different from our general horizontal motion, right? We have two subtle changes in here. Number one deals with our acceleration. Horizontally, again, we didn't always know the acceleration. When we're in free fall, so only under the influence of gravity, that is the only force that we consider to be acting, our acceleration becomes G, the acceleration due to gravity, negative 9.81 meters per second squared. Important little piece here. G is not gravity. G is the acceleration caused by the force of gravity. This negative 9.81 meters per second squared is an acceleration. It is the result of the force of gravity. Okay? So G is not gravity. G is the acceleration due to gravity. Again, I'll go back to the previous slide. As objects fall, the acceleration due to gravity, G, is constant. So here, same deal, right? G is the acceleration due to gravity. We know that value, it's negative 9.81 meters per second squared, which is then really nice when we start solving through with any formulas because we automatically know one of the variables. We know G. The second thing that we do, right, how we kind of change the general horizontal formula to help match vertically, is we start using y's in places. So instead of calling it delta x, we refer to it as delta y because, again, that y tells us vertical motion, x tells us horizontal motion. So in the general formulas to the left here, wherever you see delta x, note in the right-hand column where it's vertical, now we see delta y's. To help differentiate our velocities, on the left-hand side we had VI and VF to represent initial and final velocities. Now in the vertical column, we go VYI and VYF. That indicates we have an initial vertical velocity or an initial final, or a final vertical velocity is what we would have. And the way that it's good to read the subscripts is you can read them backwards from right to left. So if you look at the top vertical formula there, that VYI would be read as the initial vertical velocity. So I for initial, Y for vertical, V for velocity. Initial vertical velocity is VYI. VYF would then be read as the final vertical velocity. F for final, Y for vertical, V for the velocity. And the one variable that doesn't change is time, right? Time doesn't change because time doesn't care whether you're moving horizontal or vertical. Time is going to be time. No matter which direction you're moving, that time is going to continue to pass. So what we can see here based on free fall is we have objects that are solely under the influence of the force of gravity, which then results in the acceleration due to gravity of negative 9.81 meters per second squared. And we can modify our general formulas to get our vertical formulas.